Welcome to the second part of the training on Siemens biogeochemical products for the Baltic Sea. In the previous Jupyter notebook, we saw how to plot maps of biogeochemical parameters from the monthly Siemens model products for a selection of dates, for a regional zoom, and for the whole period that was contained in the product, which was the 2-year period of 2016 and 2017. In this notebook, we see how to plot time series of the biogeochemical parameters at different points in the Baltic Sea from the monthly Siemens model product. So compared to the previous notebook, in this one, we choose to select different points and to follow the evolutions of selected parameters over 2 years on this point. So first, as usual in Python, we need to import the modules we are going to use in the notebook. We're going to use the operating system interfaces, X-array, and matplotlib modules. So let's import the modules. In this part of the training, we are going to work with the same product as in the previous notebook. And we are going to focus on the 4 points that are defined on these figures: point 1, point 2, point 3, and point 4. Of course, after this exercise, you can try to obtain time series for different or more points than the one studied here. You'll just have to change a couple of variables that are defined in later cells, and you can also reduce the time span and choose to study only 1 year, for example, by playing with the date variable that is defined in a later section. So, as in the previous notebook, we first start with defining the directory where our product is, data model. Then we define the model file name, which is the directory plus the file name. Then we declare the parameters we are going to work with. In this notebook, we chose to focus on the chlorophyll and oxygen concentration and the nitrate and phosphate nutrients concentration. Then we store all the variable names in an array in order to be able to loop over the parameters when we are generating our figures. Then, last action of this cell, we declare the directory where we want our figures to be saved, and we create it if the directory doesn't exist. Then, the next cell, as in the previous notebook, is just used to open the Siemens biogeochemical product and store it in an X-array dataset called FEM that we're going to see the content. So here you should recognize what we saw in the previous video. These are the same dimensions, the same coordinates, and the same data variables, which makes sense because we're working on the exact same product. The following section is dedicated to generating, showing, and saving the time series plot. As I said at the beginning of the video, we will consider 4 points with the following longitude and latitude coordinates. These points are the theoretical points, but in practice they may not be present in the product, at least not with the exact same coordinates that are defined here. So for each point, we have to find the closest point in the product. We first create a longitude and a latitude arrays to store the longitude and the latitude values of each point. So here you can see the longitude coordinate of point 1, and here the latitude coordinate of point 1, and the same for the 3 other points. Then with the cell function of X-array, we select the closest points to the points defined here in the product with the method nearest. We store the 24 dates available in the product in var time. We create 2 arrays to be able to generate more conveniently our figure in the next cell, and we display the resulting X-array dataset after the cell function. So you can see that the resulting X-array dataset only has 4 latitude values and 4 longitude values. All variables remain. Let's check, for example, the longitude values. You can see that for each longitude defined in the LonPT array, there is now only the closest longitude value from the product. Last step, we are going to generate the figure. So this cell, cell 4, creates one figure with 4 subplots, with 1 subplot or 1x per variable. For each variable, it will be then possible to see the time series of this variable at each point location. First, we create our figure with the subplot function, and this figure has 4 axes on 2 lines and 2 columns. Then we loop on the parameter name, the array we defined at the beginning. So each parameter variation for the 4 points will be displayed on 1 axis. So 1 axis, each axis is dedicated to 1 parameter. And then on each axis, we will display the parameter variation for each point. You can see that here we are working with the FENPT dataset with the variable P on the 24 time frame for the latitude and the longitude of the point. Then we set the properties of each axis: the grid, the legend, the title, the label. And finally, we save our figure and display it. So we can see that we generated a figure with 4 subplots, 1 per variable, and each subplot displays the evolution for 2 years for the 4 points. So what do we see on these figures? We can see that an increase in nitrate and phosphate concentration in May 2016 and 2017 is followed by an increase in chlorophyll A concentration in summer 2016 and 2017. Then the nitrate and phosphate concentration decrease in summer 2016 and 2017 as they are consumed by the phytoplankton. The algal bloom is then followed by a dramatic decrease of the oxygen concentration in the Baltic Sea, and this may lead to a eutrophication phenomenon. On the chlorophyll subplot, you can see that the location that is experiencing the highest chlorophyll A concentration is 0.1. And as a reminder, 0.1 is the point located in the Gulf of Riga. And we had already identified this area as one of the most affected by algal blooms in the previous notebook. The second step of the training is finished. Let's move on to the third step.